We have finally arrived at the very last lesson of this chapter, which means you're going to get the opportunity to show me what you know on a test very soon. Chapter 2, Section 7 deals with percent error, and the proposed goal, we don't have one. How about that? Pacing guide, however, is 45 minutes, so we should be able to knock this out in a single class period. Estimation is used many times during the course of your day. You may estimate how much your lunch will cost at a restaurant. You may estimate the number of jelly beans in a jar at a carnival. Estimates are going to be a lot more valuable the closer they are to the actual amount. How can you use percents to describe how close you are to an estimate is to the actual amount? That is going to be the point of this lesson. And check this out. We only have 7 resources. Maybe this one will go quick. How can you use the amount of error and percent error to help you know if your estimates are reasonable? Well, let's dive into it and find out, and we get to use all kind of cool tools. In this sketch, you will be using percents to investigate how close your estimates is by comparing the estimate number of an archery target hits to the actual number of hits. The target area is the smaller rectangle inside the outline box. The arrows will be shot inside the outline box only. The percent error is going to round to the nearest percent. And how we're going to use this sketch pad, this is brand new stuff to me. It says enter your estimated hits out of 100 in the space provided. After we do that, we're going to press the shoot arrow 100 times button, and then we're going to reset to clear the target. Okay, that sounds pretty good. So record the responses. How many hits out of 100 did you estimate? How many actual hits were there? What was the amount of error? In other words, how far off was your estimate? And what percent error is this for the estimate? So first off, let's pick a number. How many times do we think we're going to hit the target? Well, I'm looking at that big green screen, and I'm in the little blue box, and I'm thinking that that blue box probably takes up about 25% of the green screen. So I'm going to estimate 25% hits. Whoop, nope. Let's try that again. That did not work right. 25. There we go. I'm going to estimate we're going to get 25 hits, and now we're going to shoot our arrows 100 times. Ooh, there's a bunch of missing going on there. Still a bunch of missing going on there. We're up to 60 attempts. Alright, out of 100 attempts, there was 21 actual hits. The amount of error was 4. I was stinking close. I was close. And the percent error is a 19% error. Now, if you get bored and you want to try this at home, do it again, hit the reset, go for it. The big question in all this is, where did that 19% come from? That's what we get to calculate when we do this problem. Alright, it looks like we're going to repeat this experiment again. This time they're going to shoot 200 times at the target. Will you keep the remaining estimate or change your estimate based on the results that you found from shooting 100 arrows? I think I'm going to change my estimate. I was shooting 100 arrows, they hit 21 times, so I'm thinking shooting 200 arrows, I'm going to pick 42 times. We're going to double the number of hits, and we're going to see what happens. So right here, I'm going to change that to 42, and now we're going to shoot 200 arrows. It takes a long time to shoot 200 arrows. Alright, they're getting close to my 42 hits. Oh, I think they're going over. A little bit. I got even closer. How about that? I only missed it by 2 this time. The amount of error was 2. I estimated 42 hits. We got 44 hits. That was a difference of 2, which was an error of 4.5. Now, based on these two experiments, what would be a reasonable estimate for the number of hits for 1,000 arrows? Explain. Now, I'm not going to waste your time typing, but here's the deal. 100 arrows had 21 hits. 200 arrows had, I think, 44 hits, which means half of that would have been 22 hits. So, if I had 10 times as many shots on the first one as it had the second, I'd say probably somewhere in the neighborhood of 210 to 220 times you would hit the target out of 1,000 arrows. I'm glad we don't have to wait for that experiment to happen. The final question said, how can the amount of error and percent error help you know if your estimates are reasonable? Well, the smaller the error is, the smaller the percent error is, that's going to be the more reasonable estimates. That's going to mean you're closer to getting the best guesses on what the actual numbers are going to be. And with that, it is time for some real instruction, starting with some vocabulary terms. Percent error is a ratio written as a percent which compares the inaccuracy of an estimate to the amount of error to the actual amount. So that is a vocab term. Write it down. The amount of error is the positive difference between the estimate and the actual amount. To find the amount of error, subtract the lesser amount from the greater amount. That looks like another vocab term. Suppose 800 people are estimated to attend the high school football game. The actual attendance was 1,000 people. We're going to move through the slide of the bar diagram to represent and find the percent error. So on the bar diagram, the entire bar, they have showing being the whole group of folks that showed up, 1,000 people actually showed up. That's 100% of the attendance. From there, if we broke that up into 200 sections, and the reason we chose 200, if you remember when we did this early in the chapter, 1,000 minus 800 is going to equal to 200. So our amount of error is going to be 200. And because of that, if we divided the 1,000 by the 200, we get 5 equal size slots. So that is where they got these 5 equal size boxes of 200 from. Next thing we need to go to from there, 200 people represents 20%. How much was the error going to be? That means the error is going to be 20% because 800 people showed up, 80%, 20% of the people did not show up. Why do you think it's important to subtract the lesser number from the greater number? Because if you don't, you're going to get a negative number. A contractor estimates it'll take him 16 hours to complete a home improvement project. It actually takes him 12 and a half hours. What is the percent error of the contractor's estimate? And the question is, why might a bar diagram not be the most advantageous way to solve this one? Well, the difference between 12.5 and 16, that's going to be what, 3.5? And if you divided the 16 by 3.5, does that end up being an even number of times? Is 3.5 going to 16 an even number of times? It does not. So you end up getting decimal points for how much of a percentage each one is going to be. So it's better if we had another way to solve these. And because of that, we're going to look at this new method. First off, we wanted to identify the part and the whole on these. So when you look at it, the actual amount was 12.5. The estimated amount was 16. The actual amount is going to be the whole. Okay? That's how much time you actually spend on it. The estimate, that's going to be the whole plus the part. And then the difference is going to be the 16 minus 2.5, which is a 3.5. That's going to be the part. Now, we'll go ahead and say, I think that sometimes the actual amount may be the whole, and sometimes the estimated amount may be the whole. It depends on which one's going to be larger, but we'll play with this and find out a little bit. So from there, we're going to find our percent error. To do that, they set it up as a proportion, and good heavens, she's screaming loud. So we're going to take and pause while I take a screenshot of this and explain to you what they're doing. All right, You should be able to see that a little bit better now. We established earlier that the part is going to be the 3.5. Let's see if I make a better arrow there. And the whole was going to be the 12.5. And when you divide those two, doing your long division, 3.5 divided by 12.5 is going to give us 0.28 as a decimal. That is a ratio to 100 is 28 over 100. And once again, just read the word 0 and 28 hundredths, 28 hundredths. And that means what do you have here? You're going to have 28%. So we'll go back to our problem. We'll type in our 28 here and check that. And now we can see what was the percent error. The percent error was a 28% error. Now that wasn't very hard, really, was it? You find the amount of the difference, and then you take and divide or set it up as a ratio part to whole and divide it out. Really simple assignment. For the talk about it, says suppose the actual contractor took 19.5 hours to do the problem. What part would stay the same and what part would be different? Well, 19.5 is still 3.5 hours away from the 16. So our amount of change is still going to be 3.5. But this time the whole number is going to end up being the smaller number, the 16, where last time the 16 was a part, now the 16 is the whole, and the whole plus the part is going to be the 19.5. That will be it for part 1. When we come back to part 2 of percent error, you're going to get to solve this problem you see on the screen and see if you get it right. I'm going to go ahead and stop now. Why don't you go ahead and start working on this so you can be ready when we come back.